Hi everyone, and welcome to lesson 5. So in this lesson we're going to learn about something called the uniform motion model. So we've learned about what models are, and now we're going to look at a particular type of model. So we've already looked at the particle model, and so we'll learn about the uniform motion model today. So the first learning objective is to represent motion at constant velocity using position versus time graphs, and to represent motion at constant velocity mathematically. What does it mean to say that the data follow a linear pattern? So we saw this in a previous lesson where we mapped out, or we plotted Daisy as she was moving across the track. And so when we say a linear pattern, what does it mean? Well, it depends on the type of graph. So in this graph, we call this a position versus time graph. So for instance, we have on the y-axis, we have x, so the position along the x-axis versus time. Okay, so it's a position as a function of time. And so we see how the object's position changes over time. And so we could also say that this is the rate of change of position. So from this graph, we can say that Daisy's displacement is nearly the same for each time interval. And so between 1 second and 2 seconds, for instance, if we looked at it very closely, if we looked at the table that we made, we saw that Daisy moved 22 centimeters. And then between 2 and 3, Daisy also moved 22 centimeters. So we could say from this information, from this line, that Daisy is moving at a constant velocity. And so when we have a constant velocity, we call that uniform motion. Okay, so when something's uniform, that's indicating that it's the same, so constant. So in the previous lesson, we calculated the average velocity by dividing displacement by the time interval. On this graph, the displacement, how do we find that? Well, it is what's on the y-axis. So it would be, when we talk about graphs, we could call that the rise. Okay, so our displacement, we symbolize that with delta x. That's the rise. Okay, so how much we go up or down the x-axis, and so it was displacement divided by time interval, and so time interval is whatever the change is on the x-axis. And so time interval, that delta t, is the run. So when we find velocity, the displacement divided by the time interval, it's the rise over the run. And of course, you know from your studies of graphs, the rise over the run is the special term called slope. So the slope of a position versus time graph is the velocity. Okay, so sometimes we actually refer to position versus time graphs as velocity graphs. Okay, so let's try an example here. So let's say this graph, this is a position versus time graph. We see it's x versus t, measured in meters, m for meters and s for seconds. So we say, let's say this graph shows data collected from when Daisy was walking from the barn to her food trough. I guess I probably should have put barn door there, is probably what I meant. So calculate Daisy's average velocity. So average velocity is a change in position divided by the time interval. And so here we could really just pick any 2 points that we want because we see that it's a nice straight line. That means it's a constant velocity. So basically the velocity, the slope of that line is going to be the same as the average. So I'm just going to pick a couple points that seem to be easy spots to read. So at 4, 4, it looks like it really intersects nice and well. And the same with right here. It looks like, so that's up here. It's 4, 4, and down here looks like 2.5, comma 1.5. Okay, so this would be the final position minus the initial position, our rise, over our run, our final time minus our initial time. So which one is which? Just move these over a bit so I can have some space to work with. Okay, so this is final, and x final and t final. Okay, and then this is x initial and t initial. Okay, so x final, that 4 meters, minus x initial 2.5 meters, divided by t final, 4 seconds, minus t initial 1.5 seconds. So we get an average velocity of 1.5 meters per 2.5 seconds. Okay, so that gives us about 0.6 meters per second is her average velocity, and since it's a straight line, it's also the constant velocity. Right. So the if we think back to lesson, I think it was 3, that what a model is a simplified representation of something that's more complex. Well, we use the particle model to represent Daisy. We use that in order to make the study of her motion simpler. Well, we can likewise apply a uniform motion model to Daisy. So if you look closely at Daisy's motion, you'll notice that she didn't move at a perfect constant velocity. So for instance, her displacement was 18 centimeters during the first time interval, but then 22 centimeters during that second time interval. And so this is noticeable when we put this best fit line over the data. Right? We could see that it's not quite on the line there, and it's above the line there, below the line there. So this is noticeable. So although Daisy's motion was not perfectly uniform, it was very close to uniform. And so for this reason, we can apply the uniform motion model to her motion. And that's exactly what we did by placing the best fit line over the data. So we initially applied this model to Daisy in lesson 3 when we made a motion diagram, like we had down here. and so we saw that the dots were evenly spaced. And then we looked at this graphically, right? So we looked at it pictorially, we looked at it graphically, and we also looked at it mathematically. So we said that uniform motion is just the displacement divided by the time interval. So a few different ways to represent uniform motion model. So one thing that's especially useful about this model is that we can use it to predict where an object will be in the future. So if we know the object's initial position and its velocity, then we can actually rearrange the equation and figure out where the object's going to be after a certain amount of time. So for instance, we started off with velocity is displacement divided by time interval, and we know that displacement is x final minus x initial. And so x initial is the starting position, x final is the ending position. And so if we want to know what the final position is of an object, say Daisy, after a certain amount of time, well, let's rearrange this algebraically and solve for x final. Okay, so x final is going to be x initial plus v delta t. Okay, so if we know our initial position, and this is the uniform motion model, means it's constant velocity, so this is the same. And if we know that, and we could say, okay, after how many seconds, this is where she's going to be. So let's say, let's see, we said in the video we saw Daisy, we said she started at an initial position of 9 centimeters. And that's where she was on the track. And we said she moved at a constant velocity, essentially, of 20.8 centimeters per second. And she did so for, let's say she does so for 10 seconds. At what position is she going to be at after that, those 10 seconds? Well, we're going to add that 9 centimeters, the initial position, to the 20 centimeters per second for 10 seconds. So that will be 208 centimeters. And you should notice here that the seconds will cancel out, which is good because we want to have units of centimeters to add to centimeters so that we can get a unit of distance for our final position. And so we see here that her final position is 217 centimeters. All right, so here we have a position versus time graph. And let's say, we could say, make up a story about this. Maybe this is me driving to work. So the story might go something like this. Well, we have a straight line here from 0 to 10 seconds. Perhaps that's me. I'm just driving down the road at a constant speed. And then maybe at this 10-second time interval, perhaps I look at the clock and realize that I'm running late. And so I drive at a faster constant speed. Okay, so that slope, right, we can tell it's faster by the steeper slope, right? The rise is more over the same amount of time. And you'll practice this in your first lab, getting to know these position versus time graphs pretty well. But then at 20 seconds, we see that it's just a flat line. So does that mean I'm moving at a constant velocity? Well, in a way, but what is a constant velocity? Is it 40 meters per second? No, I'm at a position of 40 meters. But over a 10-second time interval, I'm not changing my position. So if I have no change in position, that means I'm at rest. I'm not moving. So maybe the story could be, I forgot my coffee, and so I stopped and then turned around. And so we could also say, well, what would that turning around and heading back home look like? Would it mean that the graph again goes, if I'm going at a constant velocity, does it do that? Well, thinking about position, right? I was driving toward work, so toward work, we could see that zero on the position, according to the position. Zero was my house, and as I was going to work, I was getting further away from my house, 40 meters from my house. So if I wanted to go back, well, then I have to go back toward the zero. So that's going to mean that I'm going to have to do something like this. Okay. And then let's say, what if I cross the x-axis? What does that mean? Does that mean I slowed down? Well, if the line kept going at the same slope, still moving at the constant velocity, but at this point we could have said maybe I passed my house. I wasn't thinking or something. I was too busy looking at my phone, picking out the next Cardi B song I wanted to listen to. Okay. So there's a few problems with this graph. So for example, consider at the 10 seconds and at 20 seconds. We see we're going at a nice straight constant velocity, and then bam, and another nice straight constant velocity. Well, we know that this doesn't really happen in real life, right? If we want to change speed, we have to do some sort of acceleration. If we want to increase our speed, or deceleration, or negative acceleration, we could call slowing down. So we don't actually see this in here. And what you'll see in your lab is that it's going to be more of a curvy kind of thing happening, and not just a nice straight bang. Okay, that just doesn't happen in real life. So we're not seeing the acceleration really, but when we model motion with the uniform motion model, we don't worry. We don't have to worry about those parts. So we could say, we're essentially saying, since the motion is mostly uniform, then we can apply this model to it. So it's just kind of a way to simplify things, right? Let's not worry about all that exact amount of deceleration. Let's kind of simplify things so that we can help analyze the scenario better. All right, so we studied motion at constant velocity. We simplified it by using what we call a uniform motion model. But objects rarely travel for a long time with a constant velocity. Right? It's far more common for objects for their velocity to change with time. At some point you gotta start moving. At some point you have to stop moving. So on your car, you have what we call a speedometer, and it tells you how fast you're going at a particular instant. And so you might want to say, well, why don't we call it a velocidometer? Well, if we look at it, you see, it's hard to tell in here, but you see there's units there, miles, mph, miles per hour, and then there's probably km or kmh or something there, the h probably hidden behind the needle, kilometers per hour. But what's it missing? It's missing direction. right? So that's why we call it a speedometer. Well, perhaps if the compass on your car was not in on your rear view mirror like it is in mine, I don't know about your car. Maybe it's here, with the speedometer. Well, maybe then we could call it a velocidometer, because we could easily say I'm going at 81 miles per hour north. Okay, so this is speed at just a single instant in time. And so if we say the graph here maybe represents Daisy moving at a changing velocity. Maybe she starts from rest and then she starts running, and she's accelerating up to a constant speed. And so what if we want to know what her velocity is at this time here, time t? Can we figure that out? Just at that one moment, can we figure that out? Okay. Well, it's not as simple as with the uniform motion model. And with the uniform motion model, we have nice straight lines, so the slope will tell us the speed. But we can approximate her instantaneous velocity if we calculate her average velocity in the region of time t. So maybe around here somewhere. Because remember that average velocity, that's not a V. Average velocity is displacement divided by time interval. Okay, and so if we look at this region, the smaller and smaller that the time interval gets, the better the approximation will actually be to what the speed is at that one point. Okay, and the speed at just one point, one instant in time, we call this instantaneous velocity. So like the title of this slide. And so as the time interval continues to get smaller and smaller and smaller, well, the average velocity reaches a constant, or we call a limiting value. So we can actually calculate the instantaneous velocity. This is probably the first thing you learn about in Calc 1 is about limits. Okay, so the limit as the time interval approaches 0 of the displacement over the time interval. Okay, and when we take a limit like this, you probably already know what this is. It's called the derivative. A derivative of x with respect to time. So graphically, the displacement over a time interval, it's the slope of a straight line. And so in the limit as delta t approaches 0, this actually becomes, try to draw this, a tangent line. I think I can pick this up and move it, right? No, that's not it. Got it? There we go. Alright, so something like that, a tangent line. Okay, so it's a line that's tangent to the curve at that one point. Okay, so the instantaneous velocity at this time t is the slope of that line that's tangent to the point on that graph. So these are probably things that you learned probably first week in Calculus 1, but here we're just trying to get you to understand this concept of what it is, how it relates to the derivative. Okay. All right. So after this lesson, there's the first two problems you could start working on. I think I put a star after what this graph could tell you, because I think that the last part or two of this, there's like 5 parts I think to this question, is we're not going to do to the next lesson. So if you can't figure that out, just hold off on that last part till the last lesson or the next lesson. Okay, so in this lesson, kind of pretty little short, but I just wanted to focus on really looking at these position versus time graphs at constant velocity, at the uniform motion model. So we learned to represent motion with constant velocity using these position versus time graphs. Okay, this is all the uniform motion model. And we also learned to represent motion at a constant velocity mathematically. So we had our initial, we've been looking at calculating average velocity or constant velocity for a while. We basically extended this equation a bit more by describing displacement in more detail. And we know that we can rearrange graphically, find displacement. If we know, we can find it if we know the constant velocity that the object's moving with and how long it's moving for. And we can even break apart that displacement, find the final position. Or if we know the final position, we could find the initial position it must have been at. All right, so that's it for lesson 5 then.